Okay, so let's greet each other properly. Good morning.
Good morning.
All right, this is Mr. Ainsworth. We're going to get into what's called volume by known cross sections using all of your integration techniques. So take a look at this irregular volume to the upper right here. We want to be able to figure out the volume of it from the bounds from A to B along the a certain axis right here. And so what we're going to do is to find this volume out, we are going to start slicing it, okay? Slicing it into pieces in which we can find the volume of it. So let's review a couple things from basic geometry, okay? First of all, let's take a look at this one piece right here. And you'll notice that the little orange area right in through here, okay, that represents its cross-sectional area. We call that A of x, okay? That's called the cross-sectional area. Okay, in each problem, what we need to do in order to figure out the volume of anything is to figure out its cross-sectional area. And then we need to figure out how thick that slice is. Now the thickness is right here in blue. Okay, that's your thickness called delta x. Okay, why delta x? Well, it's going to be calculated by the difference of 2x values. All right, in the integral, that's going to be equivalent to dx. Okay, so the width of the slice is actually a delta x, or a distance between two x values, but in the integrals we're going to find out that's going to be representative of our dx. But how do you find the volume of a piece where you know the cross-sectional area and you know how thick it is? So let's go back to geometry for a second. Let's recall something here. Okay, recall the cylinder. Okay. As you guys know, a cylinder has a circular top base and a circular bottom base. The top base is pretty much synonymous with the cross-sectional area of the slice that I'm talking about up here, and it has a certain height, and the height is the distance right here. We'll call it h. And if you guys recall how to find the volume of a cylinder, what do we do with it? What's called base area and the height? You guys remember what to do with those two? Yeah, you multiply what times what? Yeah, base area times height. So the volume of a cylinder is the base area times the height. Base area, okay, times the height of it. Okay. So for us, the volume of every slice, even though it's not a perfect cylinder, it's not cylindrical, because the shape of the slice, it's going to vary depending on the volume that we're talking about here. It's still calculated the same way. So instead of base area times height, it's cross-sectional area times thickness, okay? So the volume of your slice, like right here, let's put it over here, slice volume, is going to be equal to your cross-sectional area, which I call A of x in general, okay? A stands for area, of course, so A of x stands for cross-section area, times how thick it is, okay, and which I call it delta x. Because that delta x is actually just x2 minus x1. It's actually a distance between two x values. Okay, so it's cross-sectional area times thickness. And this is the thickness right here. And this is your cross-section. Okay, the question is, how are we going to calculate the volume of it? Okay, so what we want to do, if you notice from figure 1, this is called figure 1, this is figure 2, figure 3, figure 4 here. If you notice by looking at figures 1 through 4 from left to right, you notice how the original volume in the upper right has been sliced into more and more pieces, where the pieces become thinner and thinner and thinner. Who notices that? Okay? And if you do that, if we slice it up in more and more pieces, the slices become thinner, the area decreases, and we're going to approximate the volume of the solid, better and better as we increase the number of slices by cutting it thinner and thinner and thinner pieces. So in calculus, we know we could do it for 10 pieces or 100 pieces, but what would be the best thing to do to calculate the exact volume of the solid? Slice it up into how many pieces? Infinite. And guess what? We can do that. We can also add up an infinite number of volumes. That's easy to do because we've learned in the past that the integral actually is representative of an infinite sum. Do you guys remember that? Okay, so what we're going to do to get the volume now, the volume of solid, Oops, I misspelled that. That's supposed to be VOL for volume. Let me fix that. Okay, so the volume of the solid is going to be found by adding, remember the sigma in algebra stands for sum. That's the sigma notation. The sum of the slices from 1 to infinity, or the sum of the slice volumes, okay, which means we got to add up the first slice, second slice, and third slice. And the way we do that is we call the first slice A of x sub I times your thickness, which is going to be your delta x. Okay, now I put x sub I there where I stands just for a counter. So when I is 1, then we have A of x1, which stands for your first slice, or your first cross-sectional slice. And then when I is 2, you have A of x2, that stands for your second slice, and so on. And you want to run that up to infinity, and then you want to add them up. Okay? And the way we add them up is we integrate using the bounds. Now let's look at the picture up here, the upper left. Your left bound right there is your bounds of the integral. Your left bound is A and your right bound is B. And we're going to be looking at those bounds in the problems that we're going to be looking at. So this is going to be equal to the integral from A to B. This is your exact volume now. Not an approximate, but actually the exact. Okay, because we're going to make them infinitely thin, and we're going to sum them up. Of AX, which just is your cross-sectional area, which is going to be found by basic geometry formulas from the past that you already know. Whoops, not equal sign there. Dx times the thickness, which is going to be dx. Now your delta x in the integral is your dx. Okay, so A of x is cross-sectional area times dx. You know, that's going to be your thickness, and then the integral sums them up from A to B. So we basically have a two-step process in every single problem. We have to calculate the cross-sectional area that we're working with. That's going to change from problem to problem. And then we have to integrate from A to B. That's step 2. And that'll give us our exact volume. So the first lesson is not too difficult. It's just a question of understanding what you're doing, because it gets kind of weird in 3 dimensions. Okay, so let me illustrate the idea. Here we go. In example 1, we have a solid's base as a unit disk. Okay, a unit disk is simply a circle with radius 1. That's this right here. Okay, it's a circle with radius 1 centered at the origin. Okay, that's what unit disk means. Okay, in the xy plane. So this right here is the x-axis, this is the y-axis. Or over here on the left, this is an xy axis on an angle. And its vertical cross-sections are parallel to the y-axis. Okay, so what we want to do is to go parallel to the y-axis, and we're going to make them squares. So what we want to do is our first cross-section is going to be parallel to the y-axis. And then what we want to do on each of these to draw it in 3 dimensions is we want to rotate the axes. So if you notice over here on the right side, I rotated the axes so that we can draw the cross-sections in 3 dimensions, because we want to extend it up off the plane. So you're going to see me do that in a full-blown example on the next page pretty soon here. So instead of drawing it perpendicular like vertical and horizontal, we rotate them a little bit. Rotate the axes, and so when we draw the squares like I'm doing up here, you can see it develop as you go from the left bound to the right bound. And what happens is you develop these squares, it actually forms a solid like indicated in these pictures here. So you can see if in the first diagram here, in diagram number 1, you know, it's been divided up and it looks like 8 or 9 slices where the cross sections are squares. You know, this is a square right here. All right, and the more you divide it up, or the more squares you divide it up into, where the thickness decreases, it approximates the shape in the third figure down here. All right, so you really want to slice it up infinitely thin so you develop the solid from A to B. The question is how you do that, how you calculate this volume of this irregular solid generated where the cross-sectional areas are squares. So here's how you do it. Okay, what we need to do is figure out the length of this square. That's the side of the square right there. We need to figure out that length. Okay, to do that, you need to figure out this distance here on the unit disk, or on the base. This is the base. And that's easy to do. All you have to do is just solve for y in the function. Okay, so let's do that. You subtract x squared, and you get y squared is equal to 1 minus x squared. To solve for y, we We square root, and we get y is equal to plus or minus the square root of 1 minus x squared. Okay? So this y value right here at the top here is the positive root, 1 minus x squared, the root of 1 minus x squared. And down here at the bottom here, this y value down here is going to be y is equal to negative of the root of 1 minus x squared. So the negative root is the lower half, and the positive root is the upper half. The question is, what's the length of the side of the square? So look up here, because I got to point with my fingers here. This is the square root of 1 minus x squared. This is also the square root of 1 minus x squared. The question is, what's the total length of one of the sides of the root? So this right here is the same as this. What's the total distance here for this side? What do you do with the root of 1 minus x squared? Okay, times it by 2. Who's with me on that? All right, so the root of 1 minus x squared plus the root of 1 minus x squared is just 2 times that root. So the side of the square, really, is just 2 times the root of 1 minus x squared. And you need to know that because the area, or the cross-section area, since it's a square, depends on the side. Does that make sense? Okay? So, and then the question is, what are the bounds? Because right here, this is, well, right here, this is negative 1, and this is positive 1. Because it's a unit disk with radius 1, where this is A and this is B. So A equals negative 1 and B equals positive 1. Those are your left and right bounds in the integral. Okay? Okay, so we're going to step it out. Here we go. We're going to find the cross-sectional area first in every problem. Okay? If it's built by squares, then you need to find the area of a square. And how do we do that? Given a side. What do we do with the side of the square to get the area? Yeah, you square it. It's side squared. So the area formula for a squared is just side squared. And for us, well, it's 2 times the root of 1 minus x squared. And we got to square that. Now, before you put that in the integral and integrate it from negative 1 to 1, what you want to do is simplify your cross-sectional areas first so the integral is a lot easier to handle. So let's square this guy first. We square the 2 to get 4. And when you square the root, they cancel, right? Giving you just the 1 minus x squared. So you get 4 times 1 minus x squared. 4 times the quantity of 1 minus x squared. You got to square both the quantities inside the parentheses. Give me a thumbs up if you're with me so far. Okay. And even though it's a video, guys, you got to remember that you can jump in with questions anytime. I'll just repeat the question and then answer it on the video so people watching can hear it. Okay. So this is your A of x, right? That's your cross-sectional area. This right here. This is your A of x. Now its thickness is right here. That's your delta x or your dx in the integral, your thickness. Your bounds are where you start and finish. Okay, so you're starting at negative 1 and you're finishing at positive 1. So over here, back here, A is equal to negative 1, and right here, since the radius is 1, B is 1. So you have to know your bounds, and that's going to be given in every single problem. Okay? So here we go. Let's get the volume now. We're going to integrate from what to what? Okay, negative 1 to 1. Cross-sectional area A of x times the thickness. So 4 times the quantity 1 minus x squared. That's your cross-sectional area times its thickness, dx. Okay, now this is a circle, and the base is a circle, and circles have symmetry. So you can simplify this integral if you want, but instead of integrating from negative 1 to 1, you could integrate from what to 1? 0 to 1, and then if you integrate from 0 to 1, what do you have to do with the integral once you're done? Double it. And it's a whole lot easier using 0 as a bound versus negative 1 because less mistakes are made and it's just easier to deal with 0. So what I suggest is you use symmetry, okay, and do it this way. 2 times the integral from 0 to 1 of the same thing. So whenever you know symmetry exists, you can use it to your advantage and simplify the integral by using a bound that's real easy to deal with, like 0. Who's with me so far on that? Okay. You don't have to do that. You could integrate from negative 1 to 1. If you're not sure, I'd suggest you do that. Okay, so let's go for it here. I'm going to bring out the 4 and write it as 8 times the integral from 0 to 1 of 1 minus x squared dx. And now I'm going to integrate from there. So here we go. We've got 8 times x minus x cubed divided by 3 evaluated from 0 to 1. And I see you guys working ahead of me. That's really good. Okay, what I'm going to do is start off with the upper bound. I got 8 times 1 minus 1/3, and then minus 0, because when you evaluate that function at 0, you get 0. Okay? Now 1 minus 1/3 is 2/3, right? So we have 8 times 2/3, which is 16/3. And this is volume, right? So it's not square units, it's cubic units, right? So this is cubic units here, whatever those units are. You know, that'd be like 5 1/3 cubic units. So this third figure here, if we smoothed it out and actually built this thing with those dimensions, would have 5 1/3 cubic units in there. So if it was made out of solid gold, you'd take, and it was in inches, it'd be 5 1/3 cubic inches. You multiply it by the cost per cubic inch, and then you get your total value. Okay? And believe it or not, this application has major, or it's seen a lot, let me put it that way, in engineering all the time, because most of the engine parts and airplane parts and, well, anything are curved. And it's important to find volumes and surface areas and other things to figure out costs and amount used and things of that nature in engineering. So all the mathematics our guys are learning right now is really applicable to engineering all over the place. Okay, so let's just review what we did. Let's go back up a little bit. What we want to do in each problem is we want to figure out what shape we're using. In this case, our cross sections are squares. Right here, they're squares. And that means that we need to figure out, how to find the area of a square. That was pretty simple. It's side squared. All right. So step 1 is we find the cross-sectional area. Right here, step 1. And step 2, we set up an integral using the bounds, and we integrate from the left bound to right bound, and we take a of x right here, which is our cross-sectional area, times our thickness, our delta x, which is our thickness, which in the integral is our dx. Okay, so step 1, find the cross-sectional area and simplify it. Step 2, integrate, and you're done. You got your volume.
How do we know what the bounds are?
They're going to be stated in every problem. But in this case, since it's a unit circle, it has a radius equal to 1, which means my right bound is 1, and my left bound over here is at -1. Okay, only because they said unit disk. But in other problems like what we're going to do right now, it's going to be really specific. It has to be stated. Okay? Let's try some more, because one example is not enough. Okay, I switched the order on these because my assignment sheet has the answers to example 1, so we're going to start off with example 2. I think it's just the next page in your handout I switched it, didn't I? For you? I want to do example 2 with you because the answers on your assignment sheet are for example 1. And I'm going to have you do example 1 right after I'm done in class together, and I want you to have answers for that. Okay, so everybody find your example 2, this one here. Okay, so here we go. And this one's different because check this out. The solid's base is not a unit disk. It's a what? It's a parabola. Okay, so the base is a parabola in the xy plane given by x equals 4 y squared. That's a parabola opening up in which direction? Left, right, up, or down? Left, right, up, or down? Right. To the right because 4 is positive. Okay, and y is being squared as opposed to x. So it's a parabola opening up to the right, and here are the bounds. Sean, you were just asking me what are the bounds? Well, here they are right here. The bounds are going to be from x equals 0 to x equals 6. Okay? So those are going to be the bounds, and they have to be given in the problem, otherwise you won't know what to do. Okay, so the first thing what we want to do is we want to draw this three-dimensionally so we have an idea what's going on. And instead of drawing the axis vertical and horizontal, we're going to rotate them. Okay, so we can draw this three-dimensionally. So here we go. Watch me as I show you how to do it for the first time. Okay, this is going to be your x-axis, and this is going to be your y-axis. We're going to rotate the axes a little bit. And to set up the integral, to actually solve this problem, we only need sketches. Okay, it doesn't have to be perfect. Now let's go back up to the parabola there. 4 is positive, the lead coefficient positive, and y is being squared. So we know that this doesn't open up or down. It opens up to the right because 4 is positive. Does that make sense? You guys recall that? So right here, let's make a note of what I just said here. This right here, A is positive, and y is being squared, so this opens right. You just have to know those basic things from Algebra 2. So when you graph this baby, it looks something like this. Just all the sketches needed here. the question is, what is the upper half and what's the lower half? So what we want to do is we want to take our function, your x equals 4y squared, and we want to solve for y, and then we can label the upper and lower halves of your parabola. So let's go for it. Let's divide by 4. Okay, we have x divided by 4 equals y squared. And to solve for y, we square root. Right? And we have y is equal to, help me out a little bit, plus or minus root x divided by 2. Square root of 4 is 2. Okay, so what's the upper half? This right up here, what's the upper half of the parabola? The positive or the negative? Positive. So this is going to be root x divided by 2, and the lower half is going to be the negative root x divided by 2. Okay, and then now what we want to do is we want to develop the solid from x equals 0 to x equals 6. Here's 0, and out here somewhere is x equals 6. Again, this is just a sketch. Okay, where the cross-sectional areas are first squares, and then we'll do it with rectangles with height 2, and then we'll use semicircles, and we'll go through the whole list together here. But the first one we want to do with cross-sectional areas, which are squares. So let's draw a few. Okay. Okay, there's the first one there. Not the first one, but it is a representative one there. Let's draw another one here. They get bigger as you go to the right, as you increase this x. So your squares get bigger, you know, as you increase, as you go from x equals 0 to x equals 6. Okay, and what's important for us is to figure out the side of the square. What's the side length equal to? And so on. Okay, so let's talk about that for a moment. Let's take a look at the distance here in black. This distance right here in black. Okay. So we're on the upper half of the parabola. This is y equals 0, and here y equals root x divided by 2. So that distance is root x divided by 2. Well, we don't need that. That's only half the length of the side. We want the full length. So what are we going to do with that distance? Double it. Okay, we don't square it, we double it, because that's root x divided by 2. So is this down here. Okay, we either add it together or we double it. So the side of the square is actually 2 times root x divided by 2. Okay, so the side of square is equal to 2 times root x divided by 2. And that's just what, guys? It's just root x. So the side length is root x. Okay, and as I said earlier in my first example, we define the cross-sectional area, which I just call a of x. We want to take the side of the square and we square it. Again, this is a square, so it's just side squared. So this is just root x quantity squared, which is real simple. What is it? And that's your area of your square in general, given a side x. Or excuse me, the side in terms of x. Okay, so there's your cross-sectional area. Questions up to this point? For every geometrical object, you have to know how to find its area, which is based upon either a side or a radius, depending on what's going on. And then you have to figure out its area using that formula. And then you want to calculate its volume, so let's go for it. Okay, we want to integrate from x equals 0 to x equals what? X equals 6. Again, it's stated in the directions. So this is A and this is B. So from 0 to 6 of our cross-sectional area x times its thickness, which in the integral is going to be dx. Okay. Give me a thumbs up if you're with me so far on that. Okay. Okay. And this one's pretty simple to integrate. Go ahead and work ahead of me. So let me see, x squared divided by 2, evaluated from 0 to 6. What are you guys coming up with? 18. Okay, 36 divided by 2, 18. 18 what? Units cubed, or cubic units. There you go. So what we want to do is get used to this idea. We're going to take the same base. Okay, it's going to be a base of a parabolic base, and then we're going to build the solid using now rectangles and semicircles, and we're going to see how it's developed. Okay, let's try it again. Let's recreate the base of the parabola. So let's rotate the axes here. Okay, sketch your parabola real quick. Again, all that's needed is a quick sketch. And this again is y equals root x divided by 2. Yep. Okay, and y equals negative root x divided by 2. But this time we want rectangles of height 2. So the rectangle's height is constant. Okay, so let's draw a few of these guys. So the width is changing, but not the height. The height's constant. Okay, so it's a different solid when it's formed from 0, x equals 0 to x equals 6. The question is, what's the length? We need this distance right here in blue. We need the length. What do you think the length is? Same or different from the previous example? Okay. What's changed in this example compared to the square? Yeah. It switched from a square to a rectangle, so the side is the same, or the length is the same, but the height's changing, right? So instead of height equal width, or length equal width, it's now the height is actually constant too. So remember, the length is the same. It's going to be 2 times root x divided by 2, or simply root x. So our cross-sectional area, given that it's a rectangle, it'd be length times width in general, right? Length times width in general, right? And the length is root x, and the width of it is actually the height, right? And that's 2, so times 2, or simply 2 root x. There's your cross-sectional area. It's just basically side times side. Length times height, or length times width, however you want to say it. Who's with me so far on that? Okay. Now, what are the bounds in this situation? 0 to 6. So again, to get the volume now, you just go ahead and integrate from 0 to 6 of 2 root x. So cross-sectional area times thickness. Go ahead and work ahead of me here. Let's check it out here. So I'm just going to rewrite the integral real quick. Take it to the half power. Let's see here. 2 times 2/3 times x to the 3/2. Evaluate it from 0 to 6. And that's going to be 4/3 times x to the 3/2 from 0 to 6. So you got to take 4/3 times 6 to the 3/2 power minus 0. Who agrees so far? Question is, what's 6 to the 3/2 power? There you go. Okay. Just let me know who had difficulty at that point right there. Okay, thanks for being honest. Here, check this out. This is how I would do it. Just take 4/3 and take 6. Instead of taking 6 to the 3/2 power, we know 3/2 is 1.5, right? So this is times 6 to the 1.5 power. Well, that's the same as taking 4/3 times 6 to the half power. Isn't that true? Because when you multiply like bases, don't you add their exponents? So I just use an exponent row there. That's 6, and that's root 6, 6 root 6. That's the easy way. You could take 6 to the 3rd power first, get 216, and then simplify root 216 to get 6 root 6. But this is quick. And then you got 24 divided by 3, which is 8, so 8 root 6. Who else is coming up with 8 root 6? Okay. No, the 24 divided by 3 is just 8. So I'm coming up with just 8 root 6. Oops, 8 root 6. Okay? Any questions up to this point? Well, let's change it up a little bit. Let's work with semicircles right now. So let's graph it again. Let's rotate the axes again. Let's draw your parabola. Remember, you got to draw the base first, and all that's needed is a sketch. But this time, the shape of it's going to be totally different. It's going to be curved above because we got semicircles. It's going to look like the upper portion of an egg or something. I don't know. We'll find out. Okay, semicircles. A football. Oh yeah. Top half of the football. Thank you.
It's an ellipsoid.
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 Oh, ellipsoid. Ellipsoid. I don't think he has it right there. Let's draw the semicircles. That was a good analogy, by the way. If you cut a football in half and you're looking at the upper half of a football, you guys see it in your mind? Yeah? So some of these are kind of hard to visualize, but we have to recall how to find the area of a semicircle. So let's go back to basics. What's the area of a circle in general? Pi r squared, right? And what do you do to pi r squared to get the semicircle? Okay, so here we go. So semicircle is going to be pi r squared divided by 2. So what we need in this problem, and this is different than the previous one. Look at this. The semicircular area relies upon only the the radius. That's this distance in blue right here. This is the radius. What's that equal to in our situation with a parabolic base? Root x divided by 2. So radius is root x divided by 2. And again, my suggestion to you is that you substitute that into your area formula first. Simplify it before you do anything. Okay? So your a of x in this one is going to be pi times radius squared. So root x divided by 2 squared, all divided by 2, or you can just put a 1/2 in front. That might be easier to write. Good luck, Sean. Okay. So let's simplify the cross-sectional area first before we integrate. We're going to square the root x to get x. Square the denominator, you get 4, so you get pi halves times x fourths, and that's pi x divided by 8. Okay? That's going to be your cross-sectional area. Okay, and now you want to integrate from 0 to 6. So the volume of this solid is going to be the integral from 0 to 6 again of pi x divided by 8 dx. So step 1, get a cross-sectional area based upon some geometric formula from the past. Simplify it first, remember that. And then integrate using your bounds. Okay? Pull out the pi 8s too if you want. You can write it as pi 8s times the integral from 0 to 6 of x dx. That might be easier. Okay. So you're going to have that equal to pi 8s times x squared divided by 2. Evaluate it from 0 to 6. And that's going to be equal to pi 16ths times 6 squared minus 0. What's that? When you simplify 36 pi 16ths, what do you get? 9 pi fourths? Who else get 9 pi fourths? Okay. So you get 9 pi fourths cubic units. Okay. How are we doing out there today? Any questions pop up in your mind? If so, speak up, okay? All right, let's do it again for equilateral triangles. This one, you may not remember the formula from the past, so we might have to develop this on the side. So let's sketch it first. Here we go. Okay. Sketch your parabolic base. Okay, but this time our cross-sectional areas are equilateral triangles. Okay, so let's draw a few. Okay, and what we need to do is, I doubt you remember this formula, but we need a formula for the area of an equilateral. Don't worry about it, I got your back. We'll develop that on the side, right? Okay, so let's do this. Let's go off to the side and let's draw an equilateral. And let's go back to geometry just for a second. Okay, so an equilateral triangle there. We need to develop a formula for an equilateral triangle that's based upon its side length. Okay, so we need, so suppose we'll call this, this is the side length. Well, let's call it x. Okay? So that no matter what x is, we have a formula for the total area. That's what I want to develop with you guys. So what we're going to do is we're going to draw on the height like we normally do in geometry. And we're going to have to kick out some, or recall some basic facts that you know about an equilateral. First of all, look in this angle right in there. Lower right. What do you guys recall about that angle? 60 degrees. Let's put it in. That means that the angle up here is 30. We have a 30, 60, 90. Okay, now if that's the case, you also have to remember that the base has been split into two equal parts. So if the original base is x, then what's this distance right here? Yeah, right. It's x divided by 2. It's half of it because we split it into half, right? Then what do you do from the short side, which is labeled x divided by 2, to get to the height, which is that dotted line up there? What do you multiply it by? Not 2. You don't double it. That's going to the hypotenuse. You double. Root. You multiply by root 3. So this right up here is actually x root 3 divided by 2. It's whatever the short side is times root 3. Okay, now let's get an area formula here. So the area of an equilateral triangle, in general, it's base times height divided by 2 for any triangle. Okay. So look at the original triangle there in red there. The base is x. This is your base, right? So it's going to be x times the height. Okay, x times the height. What's the height? Well, it's x root 3 divided by 2. And then you got to divide this by 2 again, or take half of it. Let's just multiply it by half. And now simplify it. What's x times x? Okay, so this is equal to x squared root 3 divided by what? No, not dos. Right. 4. 2 times 2 is 4. So there's your area formula for an equilateral only. Not for any triangle, but for an equilateral. That's based upon its side length. So if you know its side length is a function, all you have to do is square it, multiply by root 3, and divide it by 4, and you got the area of that equilateral. This right here has to be memorized, okay, guys? Unless you want to develop it every single time. Okay? So here we go. Let's take that off to the side. Let's get our... Everybody look at the diagram now. You see this distance here? If this right here is y is equal to root x now, divided by 2, then this is root x divided by 2. And this right here is also root x divided by 2. So this length, or the side of the triangle right here, is what? The side of the triangle is just root x. And that's equal to the side of the triangle right there. Because root x, a half root x plus a half root x is just root x. Give me a thumbs up if you're with me on that. I've kind of done that a couple times today already, right? Okay. So now that's the side length. That's equal to the side. So what we need to do is substitute it in here, because this is a side. So it's side squared times root 3L divided by 4. So my a of x, here we go. It's side squared times root 3 divided by 4. There's my formula that you have to memorize. Well, unless you want to develop it every time. Okay, so you got to take root x, you got to square it, multiply it by root 3, and then you got to divide that baby by 4. So what is that when you simplify it? X root 3 divided by 4. You always want to simplify it before you integrate. Simplify first. Okay? Simplify first before integrating. How's my speed, by the way? Am I going too fast or too slow or just right? Okay. Okay, now let's integrate. Here we go. Let's find the... oh man, I haven't asked you this in a long time. Tell me to bring it on. Bring it on. All right, here we go. We're going to integrate from 0 to 6, because those are the given bounds. All right, of our cross-sectional area, x root 3 divided by 4 times your thickness dx. That constant, that root 3 force, you can bring out the integral if you want. So if you wanted to rewrite it like this, you could, to make it easier to see. Okay, and you've seen that before. We've already done that. So we're going to have root 3/4, or divided by 4, times x squared divided by 2, evaluated from 0 to 6. It's nice that we started at 0, isn't it? Yeah. Okay. And then, so what do we have? We have root 3 divided by 4 times 36 divided by 2 minus 0. If we simplify that, that's 9. So it's 9 root 3 divided by 2. Who's with me there today? There's your volume. Cubic units. Okay? Cubic units. Okay. Now the only thing we need to do is do something weird. The last example is a weird one. We want to do the same base, a parabolic base, but this time we want a cross-sectional area that are squares with diagonals in the xy plane, which means it's not the same as our first example. The diagonal of the square is in the xy plane as opposed to the side of the square. Okay, so this picture looks different. Check this out. Here we go. First we draw. Okay, so draw your parabola. Parabolic base, as I call it. Whoops, that's terrible. Let me redo it. Okay, it's not the same as the first one. It's a square with a diagonal in the xy plane. So here we go. Let me draw one. Suppose this is the diagonal right here, and here's the sides of the square. So you got, who sees that half of the square is above and half the square is below? It's below the xy plane. This is the x-axis, this is the y-axis. So this portion, let me color code it. Here we go. This is the upper half. This should be better seen. That's the lower half. That's below the xy plane. Who's with me now on the color coding now? This is it. The diagonal, which is, here, let me put it in green. Here's the diagonal. There's the diagonal of the square. The diagonal is on the xy plane. The upper half of the square in yellow is above the xy plane, and the blue portion is below the xy plane. So it's cutting through the plane. It's hard to, you have to really abstractly see it. And then you have to repeat this, and you can do this multiple times if you wanted to. If you want to draw another one like out here, you can. You don't have to do it. I drew that too high, but there you go. And then you want to develop that. So who sees like a, instead of a smooth solid being formed, that there's going to be a ridge, like a spiny back on this one, like this forming. Who sees that now? Because it's not smooth at the top. There's a corner at the right angle, so it's going to be. How do you say it? Yeah, but the sides are. Yeah, but believe it or not, it's curved, but there's a ridge at the very top. It's kind of. I gotta find a computer animation for this thing so you can see the actual solid. When I get my hands on it, I'll show you. Maybe Mr. White has it or something. Okay, but let's set it up. Here we go. We need to develop a formula for this because we don't have one yet. That's based upon this distance here. Okay, so if you know that distance, what do you do to it to get to the side of the square? Because we need the side length. We need this, side length. So we know that this is root x divided by 2. We know that this is root x divided by 2. And we know that this distance is root x. We know that. But what is the side length? Because this is the side. Question mark. The diagonal. This is the diagonal. This equals the diagonal. But what's the side length? Because to get the cross-sectional area, we need to take the side and square it. That's what we did in the first example. But right now we have root x is not the side length. It's the diagonal length. So we got to go back to basic geometry again. So here we go. Let's draw 45, 45, 90. The 45, 45, 90 is half of a square. It's the upper half. You guys with me on that? The diagonal divides the square into two right triangles that are isosceles, and it's a 45, 45, 90, because when you bisect the 90, you get 45. This right here, this is the diagonal. And right now it's labeled root x. So the question is, what do you do from diagonal or the hypotenuse to get to the leg? Divided by, not 2, divided by root 2. So we divide this by root 2. So if the diagonal length is root x, then we have to divide that by root 2 to get to the side, where this is the side. So the side length is root x divided by root 2. And we can't leave it like that, guys. We have to rationalize it, right? Say right. So you got to rationalize it. So let's do that. What do you get? The root of what? 2x divided by 2. So that's your side length right there. Okay, and then you can find your cross-sectional area. So we did all that previous work, all that from geometry, just to get the side length. So just remember, all you do to get from diagonal to side, just do, here, write yourself a little note. To diagonal to side, just divide by root 2. It's that simple. Whatever this distance is, the diagonal, just divide it by root 2 and you get your side length. And since we're building squares, right, it's side squared. So this should be easy. Root of 2x divided by 2 quantity squared to get your cross-sectional area. And it's nice that it's a square because to simplify that, you get a nice easy fraction to deal with. And this is a little bit harder to integrate, but if you simplify it, you get something nice. What do you get? 2x divided by 4, which is the same thing as x divided by 2, and there's your cross-sectional area. Which is easy. We can integrate that from 0 to 6 really easily. So let's go for it. Let's finish up. So the volume is going to be equal to the integral from 0 to 6 of the cross-sectional area times its thickness. If you want, you can pull out the 1/2 and write it as 1/2 times the integral from 0 to 6 of x dx. Integrate from there. Work ahead of me, guys. As soon as you get it, use your fingers and tell me what you get. Nice, okay. So hang on for a minute. Now 1/2 times x squared divided by 2 from 0 to 6 is 1/4 of 36, whoops, 36, minus 0, which is 9 cubic units. Okay, hang on for... Okay, so we get a final volume of 9 cubic units in this example. Okay, now once more, this is a video, so what I suggest you do is practice these examples. You can pause me, rewind me anytime you want, and go through it again, and make sure you can understand these examples before you try anything else. Go through it again. What I want you guys to do now is the first example here. The answers are on your assignment sheet here, so let me write that down. Answers are on the assignment sheet that I gave you. Okay, so work through these, and then also check online. If you absolutely need to, you can see the full-blown solutions. Okay, so and online as well, full solutions. Okay, so give that a shot, and then practice a lot and get good at it because we're going to continue tomorrow on this in day 2.